So we know what neural networks are, and we know that we want to train them to choose good weights for them by gradient descent. The problem is, how do we work out the gradient? Because for a complicated computational structure like this, working out the gradient is not trivial. Here's an example of the kind of neural network that we're going to be working towards. It's called the Google net. And with this kind of structure, working out the gradient is something you cannot do by hand. You can work out the gradient by hand for linear regression or for logistic regression, but for this sort of structure, it's impossible, so we need the computer to do it for us. There are a couple of strategies for this to make the computer work out gradients or derivatives for us. And the first strategy is symbolic differentiation. This is basically making the computer do what we do as well. When we work out a gradient on pen and paper, we fairly mechanically follow a bunch of rules, and we can just take those rules and put them into the computer. This is, for instance, what happens when you ask Wolfram Alpha to work out some derivation for you, some derivative for you. In this example, you can see what happens if you ask Wolfram Alpha to compute the derivative for a neural network. So this is a very simple neural network with just one neuron per layer. And you can see that even for something so simple, the derivative is already a much more complicated function than the neural network itself. And this fact is compounded exponentially the more complicated you make your neural network. So this becomes intractable for very large structures. We can also go completely the other way, and instead of doing it symbolically, we can do it numerically, where we basically forget about the symbolic structure of f, the function that we're interested in, and we simply compute its output for an input and an input shifted by a small amount. And in the scalar version, you can see here, essentially what you're computing is a line through 2 points that are very close on this function. And as these 2 points move closer to each other, this line approximates a tangent line, so the slope of this line approximates the derivative at that point. This is called the method of finite differences. Problem is, if your function has multiple inputs, you need to do this separately for every input. So if you have a function with millions of inputs, as we will if we have a network with millions of weights, we would have to compute the output of that function millions of times in order to work out a good estimate of the gradient. And we need to do that once, and we need to do that for every single step in our gradient descent algorithm. So that's not feasible. So what we need is a middle ground between these two approaches, something that cleverly combines symbolic and numeric approximations of the gradient. And that is backpropagation. The secret ingredient for backpropagation is the chain rule, which is a very simple rule in calculus, in working out derivatives. So you should know it already, but because backpropagation is basically the heart of deep learning and the chain rule is the heart of backpropagation, we'll look into it with a little bit more detail. So here, just to refresh your memory, is the chain rule. If we have a function that is a composition of two other functions, so we have two functions f and g, and we compose them to make f a function of x, the derivative of those two composed functions is the derivative of f with respect to its input times the derivative of g with respect to x. And we'll be writing a lot of chain rules. So what we'll do is we'll simplify the notation a little bit by introducing a shorthand. Step one of this shorthand is to draw a computation graph, which simply tells us which value is the argument of which function. So x is the argument of g, and the output of g is the argument of f, which this graph tells us. And since we've now stored that information in the graph, we can remove that from our notation and write down the chain rule like this. We don't have to write down the arguments of f and g anymore because we can read them off from the graph and our notation becomes simplified. Now, why does the chain rule work like this? Let's build some intuition. We won't quite give you a complete proof, but we'll try and give you some intuition. And to do that, basically, we can imagine that f and g are linear functions. And if they are linear functions, they look like this. There is some value that we multiply by the input, and to that we add some constant. Now they may not be linear functions, but because we're taking derivatives, we can treat them as linear functions, because the more we zoom in, the better they can be approximated by linear functions, because they are differentiable. And if we zoom in, as it were, infinitely close, that approximation becomes exact. So within that local approximation, we can treat them as linear functions, and we can assume that there is some SF, some slope SF, and some BF that defines that linear function. And that slope, of course, is the derivative. So SF is the derivative f over g, and SG is the derivative g over x. So now to work out what happens to the derivatives when we compose these functions, and what the derivative is of f as a function of x rather than as a function of g, we can simply fill in the definition of these linear functions. So we fill that in, we multiply out the brackets, and we get this. And this function, we know that when we compose two linear functions, the result is also a linear function. We saw that in the last video already. So this function must be a linear function, by which we mean that there is some value that is multiplied by the input x, and some constant value that is added to that. Which is true if we read the function like this. So the gray part is just a constant, and SF times SG is something that is multiplied by x. So that's the slope of our function as a function of x. And if we then fill in the derivatives, we see that we get for that slope, for that derivative, exactly what the chain rule tells us. Now, we might run into some more complicated computation graphs along the way. So one situation that we need to deal with is the situation where our computation graph looks like this, has the shape of a diamond. So what we see here is two computation paths running from x to f through two functions g and h. And what we need here, the normal chain rule doesn't help us here, but what we can use is something called the multivariate chain rule, which basically tells us apply the chain rule over one of these paths. So we apply the chain rule over g, treating h as a constant, and we add to that the chain rule applied over h, treating g as a constant. So it looks like this. To get some intuition for why this is the case, we can again approximate or imagine that these functions are linear functions. So this time f is a linear function of two arguments because f had two inputs in the computation graph. So it has two slopes, one for the first input and one for the second input. And these slopes, as before, are just all the derivatives. So when we compose these functions, we can write out what happens. And we get this. We multiply out the brackets, we get this. And now we want to cast this resulting function. We know that it's a linear function. So we want to frame this in a form where there is one value that is multiplied by x and some constant that is added to that. So basically we take into brackets everything that is multiplied by x, and we get this. So this is a linear function. And the value on the left is a single value that is multiplied by x, which is therefore the slope of the function f as a function of x. And we can see that this is exactly what the multivariate chain rule tells us the derivative of f is as a function of x. And of course, we might run into computation graphs with more than two paths running between two variables. And in that case, the multivariate chain rule tells us to simply sum them all up, and we write it like this with a capital sigma symbol. And this is probably the form in which we will see the multivariate chain rule occur the most. So now we have all our tools in place. We can start looking into how to use the chain rule to help us work out derivatives. And before we move to neural networks, we'll look at a slightly simpler example first. So this is a relatively complicated function for which it might be tricky to work out a derivative. So we're going to work out a derivative in the fashion of backpropagation. Step one is to break the function up into sub-operations, which we do like this. The input x is fed to an operation a, which makes it negative, that is fed into another function b, which raises e to the power of the input, which is fed into a function c, which takes the sign, which is fed into a function d, which takes 2 over the input. And putting all these functions together, we can express f simply as the composition in order of all these functions, or written as a computation graph like this. So now we can take the derivative simply by iterating the chain rule over these functions. So firstly, note that the output of d is f, so f over x is equal to d over x. And d over x to d over x, we can apply the chain rule. First with respect to c, so d over x is equal to d over c times c over x, and this factor on the right, c over x, we can apply the chain rule again for b. So we get c over b times b over x, and again for a. So we've decomposed what we'll call the global derivative, so the derivative of the output of the whole computation graph with respect to the input of the whole computation graph. We've decomposed this into a bunch of local derivatives. For each operation, each module or function, we take the derivative of its inputs with respect to its outputs. If we multiply all of these, we get the global derivative. And in these terms, we can phrase the backpropagation algorithm very simply. So we break our computation up into a sequence of operations. Now, exactly how we do this is up to us. That's a kind of trade-off between how much you want to do symbolically and how much you want to do numerically. But given this breaking up of our computation, we work out the local derivative symbolically, and we work out the global derivative numerically. So let's see what that looks like. We start with this decomposition of the chain rule, and we work out all these 4 local derivatives. So let's start on the right with a over x. That's easy. A of x is minus x, so the derivative of that with respect to x is minus 1. The next factor, b over a, is e to the power of a. The derivative of that as a function of a is simply e to the power of a, famously. Note that we stop there. We don't fill in what a is. We are only interested in the local derivative of b with respect to its input a. Same for c, the derivative of the sine is cosine, and for d, the derivative of 2 over x, the derivative of 2 over c is a little bit more difficult to work out, but if you write it as an exponent, you will see that the exponent rule tells you that this is minus 2 over c to the power of 2. So that gives us symbolically our local derivatives. That's all we do on pen and paper. We put away the pen and paper, we put this into the computer, and we switch to numeric computation. And numeric computation means we're working out the derivative for a particular input. For this example, we just pick some input x to show this with. So we'll pick our input x equals minus 4.499. And the first thing we do is we feed it to the function to get the output of the function and to get all the intermediate values a, b, c, and d. So a is minus x, so that's 4.499. b is e to the power of that, which is 90. c is the sine of that, and we'll take the sign in degrees rather than radians, so we end up with 1. And d is 2 over that, which is 2. So that's what we call the forward pass, computing the output given the input. So now we go back to our local derivatives, which look like this. So we see here a computation with a bunch of variables, and we can simply fill in these variables with the values that we collected during our forward pass. So that looks like this. We simply fill in the values of a, b, and c, and we compute numerically this value here. And because there's a 0 in the product, we end up with a derivative of 0 for this particular input. So that, in a nutshell, is the backpropagation algorithm. It's much more accurate than finite differences because we've taken information from the symbolic structure of our formula, and it's much faster than both finite differences and symbolic differentiation because we've only worked out the derivatives locally and we've done the rest numerically. So in that way, it's the best of both worlds. With that, let's look at what backpropagation looks like for a feed-forward neural network. So here I've drawn the same diagram that we've used so far, our 2-layer feed-forward neural network. I've extended it in 2 ways. First, I've broken up the nonlinearity, so we have a bunch of nodes k now in the hidden layer, which are simply the linear collections of the inputs and the weights. To that we apply nonlinearity, which gives us the nodes h. And of course, we're never interested in the derivative of the output of our neural network. We're interested in the derivative of the loss, which means we need to extend our computation graph with the computation of the loss, so that at the very top we get a loss node, for which we can do our backpropagation. And we'll look at the derivatives of the weights of the first and second layer. We'll call the ones in the first layer W and the ones in the second layer V. And the derivative of the bias weights we'll leave for the homework. So that's up to you to figure out how to apply backpropagation for those. So what are our modules? Looking at the computation graph, we start with the module for computing the loss given the output of the neural network, computing the output of the neural network given the hidden layers, computing the activation, the nonlinear activation of the hidden layer, which in this case is a sigmoid function, and computing the first hidden layer, the input to the hidden layer. So these are our modules, and for these we will work out the derivatives with, as it were, pen and paper in symbolic terms. I'll look at V2 first. So only two of our modules or sub-operations are relevant here, the computation of L and the computation of Y. And when we want to work out the derivative of L with respect to V2, there's only one step of applying the chain rule. So it looks like this. We get L over Y times Y over V2. And these two local derivatives we can work out symbolically. So the derivative of L over Y, we can apply the chain rule in our derivation, which moves the 2 out in front, and the second factor becomes a 1. So we get 2 times y minus t. And for the second local derivative, we simply have a linear sum, so only one of the terms affects the derivative, and the v2 with respect to which we take the derivative disappears, and we end up only with the thing it is multiplied by, which in this case is h2. So this is our symbolic expression of the derivative of v2, the gradient of v2. The next step is to do the computation numerically. So we need a forward pass for the neural network. So let's add some arbitrary functions and do arbitrary values and do a forward pass for those. And then the backward pass is just a question of filling in these intermediate values into the function we derived in the last slide, giving us a derivative of minus 3.96. So the gradient update step would look like this. We multiply this minus 3.96 by our learning rate alpha. We subtract it from our current value of v2 to give us our next value of v2. Now for the weight w12, which is a little bit more complicated. All 4 of our modules are now relevant for the derivative, and when we compute the derivative of L over w12, we get this is decomposed by the chain rule into 4 local derivatives. The first we've seen already, which becomes 2 times y minus 2. The second one is different from the last slide. We now take the derivative with respect to h2, so we get v2. The derivative of the sigmoid, we can use this property. So the derivative of the sigmoid is the sigmoid itself times 1 minus the sigmoid. So we can actually use the value that we've computed in the forward pass. We can take h2, which is the output of the sigmoid, multiplied by 1 minus h2, and that's our derivative of the sigmoid. And the derivative of k2 is just x1. So this is our symbolic version of the gradient for w12, and we'll leave the numeric computation out for now. I hope you get the idea. So there's something to note here for when you implement backpropagation, which is that a lot of these values you can compute, you are computing multiple times when you're working out the derivative for different parts of the network. In this case, we note that we have computed L over Y for both of these gradients. And in fact, if we were interested in gradients with respect to other parts of the network, we see that the decomposition of L over W2 contains many other gradients of L. So if we take the first 3 elements and we multiply them together, we see that that's actually the derivative of L over K2. And the first 2 elements multiplied together is actually the derivative of L over H2. So what you can do if you have a large computation graph, and a lot of these values you're actually interested, a lot of these nodes you're actually interested in the derivative, you can walk backwards from the loss node, and for each node compute the derivative of the loss with respect to that node by multiplying its local derivative by its parent nodes. So you're walking backwards down the graph and you're accumulating the gradient step by step. And for a large computation graph, this can be a very efficient way of implementing backpropagation. For now, let's just look at a bit of pseudocode. So here we have our network again and some pseudocode for how we might implement this in a language like Python. So we can imagine all the layers being represented as arrays containing float values. We're not yet using any library like NumPy, that comes later. And this illustrates how to compute the backward pass of the network. And notice that here already we're being a little bit clever in that we are only computing particular gradients once. So the gradient of y is computed once and then reused in the computation of the gradient of v over v and over h. And that computation of the gradient over h then is used in the computation of the gradient of w. So already here we see this walking backwards down the graph. Now, to finish up, let's see if we can build some intuition for exactly how backpropagation tunes these weights. To help us do that, here's a simple forward pass with some fairly arbitrary values filled in. And we're going to look at how backpropagation changes the weights from the top to the bottom. And we'll start with the parameter y, with the output of the network, y. And we're going to imagine, to help us build some intuition, we're going to imagine that y is a parameter. Now it isn't. It's derived from our parameters. We don't have direct control over the value of y. But if we did, how would we want to change it? If it were a parameter, we could change it by gradient descent. And the update rule would look like this. We would change y by subtracting a learning rate multiplied by the derivative of y, of the loss over y, which looks like this. So for these values, here we have an output of the network of 10, a target value of 0, and a loss, therefore, of 100. It's the difference between these two squared is the loss. So in this case, the derivative of the loss over y becomes 20. So we multiply that by the learning rate alpha, and we subtract that from our current value of y, which sort of corresponds to our intuition here, because y, as you can see, is too high. It's 10 and it should have been 0. Y is too high, so we need to decrease it. We see here that we do indeed subtract a small value from y to lower it. Now note that despite the fact that the loss doesn't care about the sign of the difference between the model output and the target, the derivative does care about the sign. So what we see here is we have reversed the situation. So the network outputs 0 and the target value is 10. So the output is too low. We note that the loss is still the same value. But if we now apply the update rule, we see that if we take the derivative, we are computing y minus t, which is minus 10. And that minus cancels out with the minus in the gradient descent, and we end up adding a value to y, which is very intuitive because y was now too low, so we need to increase it. So in this way, backpropagation very naturally takes care of the signs of our values. So we can now work back down the network to the parameters we do actually control, like v2. So here's the update rule for v2 that we've worked out earlier. And to look at exactly what v2 does, let's look at how it combines the three different nodes in the hidden layer that the v parameters act on. So here we filled in some arbitrary values for the activations of the hidden nodes, h1, h2, and h3. We've given them values 0.1, 0.5, and 0.9. So if we apply this rule here to these values, we get these update rules, 3 different update rules for the 3 different weights in the last layer. And what you see is that the node updates are scaled by the output. So if we think of the outputs of the hidden layer as fixed, we can see that the different weights contribute in different ways to the output y. Back to the situation where the output of the neural network is 10 and it should have been 1, so we want to decrease the output. So what we do is we look at these values h and see which one of them contributed the most to this output, and that one is decreased the most. So here we see that v3 contributed by 0.9. So that one is decreased more than the other V values. Now the activations we've used, the sigmoid activations, can only give us values between 0 and 9. But if we use a different activation, like the what is known as the tan H activation, for instance, we get values between -1 and 1. And in this case, we can see that the backpropagation also works to take care of the sign in a very natural way. So here the middle node has a negative value, -0.5. And what we see is that in the gradient update, this -0.5 cancels out with the subtraction of the gradient in the gradient descent, and we end up increasing V2, which is very natural because remember, the value y is a weighted sum over the values h1, h2, and h3. And these weights tell us how much each of them contributes. Now we want to decrease y. Y was too high. We want to decrease y. And one of these values is negative. So that negative value, we want to boost the weight of the negative value so that y gets lower as a result. And that happens very naturally because of this backpropagation. So now we move back down to h2. And here, to build our intuition, we use the same trick we used earlier. So h2 is not a parameter of our network. We don't have direct control of h2. But we imagine that we did. Imagine if h2 was a parameter, what kind of update rule would we end up with? Well, that's this update rule. And what we see here is that if the weight that is attached to h2 is negative, again, we get a very natural update. So we, in setting h2, we assume that the rest of the network is constant. So we assume that this -3 is given. We don't get to change that, but we do get to change h2. In that case, what we should aim for is to have h2 become bigger, because we want to decrease y. So in this term that h2 is part of, we want that term to be as small as possible. One part of that term is negative, so the other part should be as large as possible. So we want to increase h2. Moving one step down even further, we see here how to take into account the effect of this sigmoid activation. So as you remember, the derivative of the sigmoid activation is the sigmoid function times 1 minus the sigmoid function. And I've drawn here what that looks like. So the orange line is sigmoid, the blue line is 1 minus sigmoid, and if you multiply the two, you get the purple line on the bottom, and those are our derivatives for the sigmoid function. So that is what the multiplier is at the end there. And what we see is that if we're in the middle, this multiplier is as high as it can be. But if we're at the end, if we're at the edges, the sigmoid function, as it were, resists changing. So the further we are out to the edges, closer to 1.0 or 0.0, the less the function wants to change under this update rule, because this multiplier h2 times 1 minus h2 gets smaller and smaller and smaller. And this effect is actually one of the big reasons why the sigmoid function was slowly replaced by the ReLU function as the default option for the activation of the hidden layers. Because once your network gets into a situation where the values are at these extreme ends, it stops changing very easily, and your learning sort of stalls. So this is actually an effect we don't want, and we change this by changing our activation. But for now, we can just move down and see what the effect is on our last parameter that we can actually change, which is this familiar update rule for W12, which we've seen before. So if we fill in our values, we see that there are now two negatives. So the input of x1 is -3, that's a negative, and the weight from h2 to y is negative. And because of these two negatives canceling out, we end up subtracting again. In short, we want to lower y, which means we want to increase the value of h2, because that one is multiplied by a negative value. Therefore, we want to decrease the weight W12, because x1 contributes negatively to that weight, and we want to increase it. So these two negatives cancel out, and we end up doing a gradient descent step again by subtracting. So that's backpropagation in a scalar setting. To recap, it's a method for computing derivatives or computing gradients, which we combine with the method of gradient descent in order to train our model. And it forms a very natural middle ground between symbolic and numeric computation, which takes the error and slowly works it down the network, starting from the output node. In the next video, we'll look at how to speed this up by phrasing it entirely in terms of familiar linear algebra operations like vector addition and matrix multiplication.